Hello everyone. This is Shruti. I'm a PhD scholar in Department of Chemistry in IIT Bombay, and I'll be your TA for this course, Ultrafast Laser Spectroscopy, which is taken by Professor Anindya Datta from the Department of Chemistry itself. And I'll be taking the live sessions every Tuesday from 7 to 9 p.m. And we'll be discussing the assignments which are given along with the lectures. Okay. So, can you guys introduce yourself? Ruxana and Sebin.
Hello, ma'am.
Hi. Hi,
Am
Sebin.
I audible?
Yeah, you are audible.
Yeah. I completed my postgraduate from CMS College, Kottayam.
Okay.
So now I am preparing for doing PhD abroad. So my master's thesis was based on ultrafast spectroscopy.
Okay,
I
great.
had my major in physics and did my master's thesis in Cochin University of Science and Technology.
Okay. So, Sebin, have you taken this course earlier, or this is the first time you're taking it?
This is the first time I'm taking the course.
Okay, fine. Did you watch the lectures in the first week?
Yeah, I completed the lectures and assignment as well.
Okay. Did you take the assignment already?
Yeah, I completed the assignment of week 1.
Okay, fine. So today, week one's last submission date is still pending. So I'm not allowed to discuss the assignment before the submission date. So today I'll be discussing as a week zero assignment, like the practice assignment itself.
Okay.
And Ruxana, can you introduce yourself?
Hello, ma'am. I am Ruxana S. I am also an postgraduate in applied physics from CM's College, Kottayam. Sebin is my classmate. Um, uh, I completed my master's thesis from Cochin University in femtosecond laser surface structuring.
Okay.
To attain a PhD position in abroad, I joined this course.
Okay, fine. So you both are classmates and you both have the same goal to get a PhD abroad. Nice.
Yes, ma'am.
Okay, fine. Uh, okay, so let us start actually. So the initial lectures are very basic ones. So the first, I'll be discussing assignment 0 today. So maybe this is the like very basic brush up for you guys today, because like the first assignment, the 0th assignment actually is very easy. It's just the basics. Okay. So I'll be asking you guys to solve along with me, and you can share the answers, right? Then we'll solve together if you are facing any problem.
Okay.
Okay, ma'am.
Yeah. So the first question is, the wave number of a transition ground state to excited state is 31250 centimeter inverse. What region of the electromagnetic spectrum does it correspond to? Okay, so how do we approach this?
I think that the wave number is given and we are asked to find the which electromagnetic region it is up to.
Yes. So now the wave number nu bar, which is inversely proportional to the wavelength, right? So
Yeah.
this is given 31250 centimeter inverse is inversely proportional to this. Okay, now this is very simple, that to get the wavelength, which is lambda, you need to take a reciprocal of this, but which is in centimeter inverse. Okay, and here I have attached a picture for you guys. Generally we report the wavelength in spectroscopy in nanometer. If we are reporting the wavelength, we report it in nanometers. So we will convert this into nanometer, right? So okay, now from centimeter, so this is how much? 1 centimeter, right? Now centimeter to meters. 1 meter is how much? 100 centimeter, right? Then from I'm converting it to meter so that for me it's easier to convert into nanometer from meter, right? So now 1 meter is how much? 10 to the power 9 nanometer. Now I can easily do the cancellation. So centimeter gets cancelled away, meter and meter gets cancelled away. So the resultant will be 1 upon 31250 into 10 to the power 9 divided by 100 nanometer. So what you get is 3125 into 10 to the power. So I'm cancelling out the zeros. So 3 zeros gets cancelled away from this. So we will be left with 10 to the power 6. Now, how much is this? Can you guys calculate? 1 upon 3125.
Ma'am, I didn't understand the meter to nanometer conversion.
Okay. So,
Is that a 10 to the power minus 9?
yes. So, let me see. 1 nanometer is how much?
10
In
raised to
meters.
minus 9 meter.
10 raised to minus 9 meter, right? If I take the reciprocal, 1 meter will be how many nanometers? So to get 1 meter, what you need to do is you need to divide it by 10 to the power minus 9. Here also 10 to the power minus 9. Then what you are left with is 1 meter this side equals to 1 upon 1 by 10 to the power minus 9 nanometer, which is 10 to the power 9 nanometer. Okay.
Okay.
So here what I did is I divide. Now these numerator and denominator is equal. So this and this is equal. So I am multiplying and dividing by 2 equal. So it doesn't change my value. It is just converting the units.
Okay.
And same thing I did with meter and centimeter. Okay.
Okay.
Next is, what is the answer here? This is in nanometer. Can you just divide 1 by 3125? What is it?
3.2 into 10 raised to minus 4.
3.2 into
10 raised to minus 4.
10 raised to the power minus 4 nanometer.
No, ma'am, into 10 raised to 6 nanometer.
Okay. 10 raised to the power 6 nanometer. Is it this much?
No, ma'am.
Let me.
10 raised to 2 nanometer.
Yeah.
3.2 into 10 raised to 2.
Three. Sorry. 1. So 1 divided by 1 divided by 3125. So it is 0.00032 into 10 to the power 6 nanometer. Now this is 320 nanometer. Is it fine?
Yes, ma'am.
Okay. Now you see this is the picture which I have given here. Can you see the picture?
Yes.
Yes.
So this is the scale which shows the electromagnetic spectrum with their corresponding wavelength. Now you see between 3 to 0 nanometer, it lies here, right? Somewhere here. Now in the visible starts from 400 to 750 or 700 nanometer. So before 400 we will have 320 nanometer, right?
Yes.
And that stands in ultraviolet spectrum.
Travel.
Yes, here. So here the correct answer will be ultraviolet. So this will be your correct answer. 320 nanometer is UV. You cannot see it through your naked eyes. We can see only the visible range. Okay. So if you have a laser of 320 or 360 nanometer, will you be able to see the laser line?
No.
No. Yes, right, that's correct. So we won't be able to see. So suppose if you have a setup, optical setup to align, then how will you align that setup if you are not able to see where the light is going, or where is it getting reflected from a mirror, where is it passing through the lens, right? It's very difficult to do that, right?
Yes.
So it's absolutely blank. That light is coming, that you know, because the laser is on, but it's very as in harmful also. UV light is harmful for your like skin and all, and similarly IR range is harmful. Infrared, if it goes somehow by mistake, if it goes in your eyes and all, it can damage if the power is very high. So to detect such light, what the laser companies do, they mix the visible range, one of the visible wavelength along with the UV light. So suppose if you have a laser of 360 nanometer, okay, so this one is not visible through naked eye. Now to align this way, this laser into some optical setup, you need to see where the line is going, where the laser light is going. Okay, for that we need to mix some laser light through it, which is visible. So we mix visible wavelength. Example is, suppose we will mix 440 nanometer, or which is visible. So you can see that 440 will come somewhere here. So 440 will be somewhere around here, this part, right? So this part you can see little violet shade is there, right? So little amount of little percentage, if 360 is like two parts, this will be one part of it, just to see the path where the laser is going. So that's why all the UV lasers will look little violetish in color, so that you can detect where it is, where the laser light is coming from and where it is getting reflected and all, so that you can save yourself from the exposure to the laser light. Okay, now let us move to the next question. So the first question is clear to everyone, right?
Clear.
Yeah. Okay. So the next one is, as per Lambert-Beard law, on which of the following factors does the absorbance not depend? So what is the answer? Have you guys solved it?
Color.
Yes, color. What is Beard-Lambert law or Lambert-Beard law?
Absorbance is
Absorbance
equal.
is equal to epsilon CL.
Yes. So A absorbance is equals to epsilon times CL. Also in terms of log, what is it?
Log I0 by 80.
Yes. So this is log 10 I0 by IT. What is I0?
Incident intensity.
Yeah, incident light. And IT is
Transmitted light.
transmitted. Okay. So you see that in this relationship, what is this?
Molar extinction
Extinction
coefficient.
constant.
Yes, molar extension coefficient, which is given here. So it depends on molar extension coefficient, and C is concentration. So it depends on the concentration as well. And L is the length through which the light travels through the sample. So this is the L. Okay. Oops. I have no power. One second, guys. I have no charge in my laptop. Just a minute. I'll just stop it for 5 minutes and then we'll resume. I have to get the power
Okay.
point. You can solve the other questions by then. Okay.
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 Hello. Are you guys there?
Yes.
Please solve the next question by then. I'll join you guys in 5 minutes. The video will be on itself. Okay.
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 Sorry for this, but the charger is not here. I'll just get it. And please solve the next two questions by then. Okay. Okay. So is this clear? This question?
Clear, ma'am.
Yes, ma'am. It's clear.
Okay. So the next one is shift to the spectrum maximum peak position to higher wave number corresponds to what? Shift to spectrum maximum to higher wave number corresponds to what?
Shift to lower wavelength.
Shifted to lower wavelength.
Yeah, so wave number and wavelength are inversely proportional. So higher wave number means lower wavelength. Okay. Energy which is given by h nu or hc by lambda, or again we can write it as hc nu bar, right? From this relationship we get to see that this is inversely proportional. Okay, so if nu bar increases, so lambda has to decrease. And what this shift is called?
Blue shift.
Sorry,
It's a blue shift.
blue shift, and blue shift is correct, and there is a particular name. Stokes.
Stokes shift.
Yeah, Stokes shift. So what is Stokes shift is, if I plot it in wavelength scale, so this is my initial peak position, okay, at a particular wavelength 1, but the Stokes shift will be
To lower wavelength.
this side, okay, some lower wavelength. So lambda 2 is smaller wavelength than lambda 1. Is it? No, sorry. What am I telling? Stokes shift is to higher wavelength.
Okay.
This is not Stokes shift. Stokes shift is always a higher wavelength. Higher wavelength. This is simply called the blue shift. Stokes shift is the red shift. Okay.
Stokes shift higher wavelength and to lower energy, right?
Yes.
Anti-Stokes shift to lower wavelength and
Higher and high, lower
higher
higher Stokes shift is higher wavelength. You just
and
remember
lower.
one, lower
Okay.
energy. Higher wavelength is always lower energy because energy and wavelength are inversely proportional.
Proportion.
Okay. So this is the question. Next one is magic angle for polarization. What is the magic angle?
54.7.
How do you get it?
Recently, in the class of week 2, professor was saying that you should keep the emission polarizer at an angle 54.7
Hmm.
to polarization of incident polarizer.
Okay. So the concept of this magic angle you will get to see in further lectures, like in anisotropy lectures. Okay, there it will get cleared. So basically, there is a mathematical relationship which says that 3 squared theta minus 1, this should be 0 for there will be no anisotropy then. Okay, at this angle, at with this mathematical relationship, there will be no anisotropy. So what is the angle at which we have to keep the polarizer? Will be this angle, the theta angle. So from this relationship we can get this angle. 3 cos squared theta is 1. and then cos squared theta is equals to 1 upon 3, which gives cos theta is equals to 1 upon root 3 plus minus. So theta is cos inverse plus minus 1 upon under root 3, which comes as 54.75 degree. Okay, so this is that magic angle of polarization. You will get to study about this in later weeks of the course. So here the answer is this 54.7. Now the next one is again a simple question, and this one is not related to this course as such. So it says that in the semi-classical treatment of radiation with matter, light is considered to be
Wave.
it's light is considered to be a perturbation and a wave.
Okay.
Because how do you treat the light matter interaction? It is the perturbation to the Hamiltonian. I think the answer is all three. Wave wave nature is also considered, and photon nature is also considered. That's why it's the semi-classical treatment. It's neither quantum nor classical, semi-classical. So light is considered, light matter interaction, light is considered as a perturbation to the system. Okay. Now coming to the next one. If a fluorophore has absorbance maxima at 385 nanometer, its emission maxima is likely to be
Greater than.
its emission maxima is likely to be greater than 385. Why is it so?
Emission is followed after.
Mhm. Do you know what is this law known as? This is a law or a rule.
No, ma'am.
So this is known as Kasha's rule. Have you heard of this name?
No, ma'am.
Okay, you can just read about it. So what it says that emission always occurs from the lowest excited state. So see this figure here. Absorption can happen to any of the first excited state. So this is your S0 singlet 0 state. This is S1, S2, S3, S4 and so on. Absorption depending upon the wavelength of light you are giving to excite the system. It can occur to any of the higher excited states or the ground excited state, which is this S1. Can have occur to here or here or here or here and so on. Okay, but the emission, which is this given by number 3, the emission always happens from the lowest excited state. So this one is the lowest excited state. Okay, so this distance is lower in energy, right, from the absorbance. That's why it is Stokes shifted. It's is that from the lowest excited state. Now this lowest excited state can be either S1 or T1. So what is S and T? This can be a singlet state or it can be a triplet state. Okay. Now if the emission is coming from a singlet state to the ground singlet state, this is known as fluorescence. And if it is coming from a triplet state, this is known as phosphorescence. Understood?
Okay.
So this is the Kasha's rule. So whatever is, so check out this figure. So if this blue curve is your excitation, the red curve, which is shown over here, this part is your emission. Now this energy is smaller. This energy level is smaller. So if energy is less, what it means is lambda will increase. So it occurs at higher wavelength. So it is happening between 600 to 650. But the absorption took place between 500 to 550. Depending upon sample to sample or your system to system, this amount of Stokes shift varies. So for some sample, this energy difference, which is given by this Stokes shift, this energy difference can be less or high depending upon your sample. Okay. So this difference, now in earlier what I told was shift to higher wavelength of the emission is called Stokes shift. So how much is this shift? So Stokes shift, the shift will be given by, suppose here it is coming at 625 nanometer and the absorbance was occurring at 525 nanometer. So 100 nanometer is your Stokes shift. The difference between the maximum of absorption and emission is known as your Stokes shift. This depends upon your sample. It may change. It is not fixed for a substance, depending upon the solvent, depending upon external environment, depending upon, like, solvent means solvent polarity and all, it changes. Have you guys heard of this name solvatochromism?
No, ma'am.
So solvatochromism is a property of a system. You guys can read about it. Depending upon the like the solvent, depending upon the solvent polarity. Okay, suppose we have a sample or a dye. That dye is shows more Stokes shift in polar solvent than non-polar solvent. It can happen like that. So if I plot, so this is the absorbance. So this is my absorbance, this red curve. Okay, the emission will depend on the solvent polarity. Suppose I have a polar solvent, example methanol. So in that case, if it is higher, then the emission will come over here. The Stokes shift is large Stokes shift. And for some non-polar solvent, it may come over here. Suppose let's take hexane, non-polar. So it is showing smaller Stokes shift. Okay, this difference is small than this difference. This depends on sample. So some sample can show the opposite behavior. In the polar solvent, it will show smaller Stokes shift. In non-polar solvent, it may show higher Stokes shift. So this type of behavior is called solvatochromism. It chroma means color, and solvato means the solvent. So the color which is given by this wavelength, the color changes depending upon the what solvent you are using. The color of the sample will change. Okay. One behavior is called positive solvatochromism. The other one is called the negative solvatochromism. So there are some particular dyes or some samples which shows this kind of behavior, and they are called solvatochromic dyes. Okay.
Okay.
So from this, you guys can read about this Kasha's rule and solvatochromism if you want. Like you can Google them and read more about them. Okay. Coming to the next one, if the refractive index of a medium is higher than that of air, speed of light through the medium will be. So what is the answer here?
Lower.
What is refractive index? How do you define refractive index? Hello?
Ratio of speed of light in vacuum to the medium.
Huh. डिपार्टमेंट का इंस्ट्रूमेंट वाला साइड पे, तो वो खराब है शायद, इसीलिए नहीं आ रहा होगा। फ्लोरोमैक्स जैस्को लिखा होगा, फ्लोरीमीटर जैस्को 370 रूम पे होगा, जैस्को का तो है। दो फ्लोरोमैक्स है, एक 360 लिखा हुआ है, एक फ्लोरोमैक्स 4 लिखा हुआ है। तो आपको कौन सा चाहिए? अच्छा, मैं अभी सेशन ले रही हूँ, मैं आपको फ़ोन करती हूँ, उसके बाद देखती हूँ, मैं देखती हूँ उसके बाद। What is refractive index is?
Ratio speed of light in vacuum to the medium.
Yeah, speed of light in speed or velocity of light in vacuum, which is c, which is a universal constant, divided by the velocity of light in that medium. Is this defines the refractive index of a medium. Refractive index of that medium is c by v. Now, if the refractive index of a medium is higher, so if this side is higher, this increases, okay, then this has to decrease, because this is a constant. How much is this constant?
3 into 10 raised to 8.
Power 8 meter per second. Okay, so it has to be lower. Now here I have given some refractive index values. Vacuum is 1 because it's 1 over 1. So vacuum refractive index is 1. Air is slightly larger, very slightly larger, almost 1. Water is 1.3. Ice is 1.31. Glass is 1.5. Diamond is 2.4. Like this. Okay. So where do you use in case of spectroscopy or microscopy? We use this refractive index values, right? Let me tell you one thing. Suppose you have, in case of microscopes, are you guys familiar with microscopes? So microscope has something called objective lens. Okay. Now this objective lens is used to see the sample through. This can be of different type. It can be air objective. It can be water objective. It can be oil objective. Okay. Now, why the objective lens is of 3 types? Because when you place the sample, if suppose this is your objective lens, okay, you place your sample over here. Now, the medium between this medium between the objective lens and the sample, if it is air, means there is nothing in between the sample and the objective lens. If it is air, the type of objective lens is called air objective. If we put a drop of water over here, over the objective, and then we place the sample, That kind of objective is called water objective. And if we place oil over here and then we place this sample, so this is the sample, that kind of objective is called oil objective. Okay. So depending upon this medium in between the sample and the objective lens, okay, we define the type of objective. This is objective lens. Now, why do we have air is okay? We have nothing in between, just objective lens and sample. But why do we have water and oil in between? Why do we place that? Do you have any idea about it?
To change the refractive index.
Yes, to change the refractive index. So, what is the main goal of this objective lens? The objective lens collects the emission or light from the sample. Okay, suppose you have some fluorescent sample over here. It is emitting light. The objective lens will collect this light and it will be then directed into your detector. Okay, so the only aim of the objective lens is to collect as much light as possible, right? So that we can see the sample or we can collect more number of signals. So this is the aim of this objective lens. If we are able to collect more and more light, the sample will we will be able to look into the sample better. Okay. Now what happens is, if we have, now this sample is on a glass cover slip. So this is a glass cover slip, right? And then here we have an objective lens. That lens is also made up of glass. What is there in between now? In between we have air. If nothing is there, we have air. Okay. Now suppose if this sample is emitting light, the light will travel through a medium. We have glass, then air, then glass. So if the light is traveling, so glass is what? A denser medium. Air is what? A rarer medium. So where it will bend? Will it go straight or will it undergo refraction?
Refraction.
So refraction will happen. Okay. So it will bend away from the normal. And again it needs the glass. So again we have a interface between two different medium. Again it will undergo refraction. So there will be a loss of light. Okay. If somehow we make this medium in between, this medium of similar refractive index as of glass, then we can, like, we will not be able to stop it, but we will be able to decrease the amount of refraction which happens, and that will allow us to collect more amount of light through the objective lens. Okay, so if you see, the glass is of refractive index 1.5 and air is 1, so there is a 0.5 difference. But if we are using water, it will be 1.3, so the difference is 0.2. So water objective, if you place a drop of water, the amount of refraction will decrease at the interface. Okay, understood something?
Yes.
Now oil, it's not written over here. For oils also, the refractive index is almost 1.5. So this, there are not all the oil, we keep particular special kind of oil. That oil is also 1.5 refractive index. So if we put a drop of oil over the objective and then we keep the sample, the refractive index matches with the sample stage, which is this, the glass cover slip, the objective, and here itself again there is a oil which has the similar refractive index. So that decreases the refractive index difference, and that helps us collect more amount of light. So out of air, water and oil objective collects the most amount of light, then water, and then air objective. Okay, so the theory of refraction is used over here in this case. Okay, now let's move to the next question. This I have already discussed. Emission without change in spin multiplicity. So you guys know this diagram, right?
Yes.
So what is this known as? There's a particular name for this diagram, right?
Jablonski.
Yeah, you're correct. Jablonski diagram. Now, what does it tell? What and all, there are many multiple processes happening. First one is absorption. Now, okay, first of all, the y-axis is energy. What is the x-axis here?
Is it population?
What is it? Okay, you guys find out what is the x-axis meaning. What is like, what does it mean? So in the y-axis, it is denoted that y-axis is energy, but what is the x-axis? Okay, you try to find out. Now, so you see that we have ground state S0 and it has multiple vibrational states. And each of the vibrational states again, so this is V0, V1, V2 and all. So each of the vibrational states will have multiple rotational states which is not shown here. Okay, for simplicity to make the diagram simple. Now ground state and S1, S2, these are higher excited states. S1 is the ground excited state. So ground excited, it should not be I should say first excited state. S1 is the first excited state. S2 is the second excited state. Okay. Now, as I told, depending upon the amount of energy you are providing to the system or the amount of energy you are exciting the system with, it can go to either first excited state or second excited state, third excited state, or so on. Okay. Now, from there can be multiple processes which can happen. The first one is internal conversion. Internal conversion means from second it can come to first excited state. from there it can either go to triplet state T1, or it can come non-radiatively to the ground state through quenching, or it can undergo internal conversion, which is also non-radiative. So this wiggly line means, this kind of wiggly line means non-radiative transition, means there is no emission if it is shown by this curly curved lines. The straight lines only, which is this fluorescence and phosphorescence, these are all only the radiative process. Radiative process means from which the light emission comes. So if it is coming from the first excited state to ground state by emitting some amount of light, that process is known as fluorescence. From S1 to S0. Now S to S is singlet to singlet, right? But if it is coming from T1, which is triplet, to S1, so this process is known as phosphorescence. Now in this case, what is happening? The spin state is changing. This is a triplet state, spin is triplet, this is a singlet spin. So the change in spin causes the phosphorescence. But if it is happening without the change in spin, which is called, shown over here, that is fluorescence. So the correct answer is fluorescence. Understood?
Yes.
So spin is conserved. In this one, the spin is conserved. Okay. Any questions here? 7.
No, ma'am. It's clear.
Okay. Nice. So I think we had only these 8 questions in the first assignment. Uh, but I have some external questions for you guys. You can note it down or take a screenshot out of it and you can try to solve it as an like homework questions. So this is the first one. The main advantage of fluorescence over UV visible spectroscopy. So why do we need to do fluorescence spectroscopy? Okay, just think and answer, and if you guys are able to do it now, we can discuss it now, or we can discuss it in the next week's lecture. Okay, the next one is this. Select the true statement about the fluorescence spectroscopy. So this is a diagram. Emission usually occurs at energy that are greater than the energies of excitation, or less than or equal to, or none of the above is correct. So what is it? This one we just discussed it.
Greater than the energy of excitation.
Yeah. So emission usually occurs greater than or equal to. Okay. Mostly greater than. So it is shown in this figure. So this is the correct one. Okay. Next one is a metabolite M was isolated from the cerebrospinal fluid. After excitation at 280 nanometer, the material fluoresced at 360 nanometer. The Stokes shift for the assay will be
80 nanometer.
80 or minus 80.
80.
Yeah. So Stokes shift is emission wavelength minus the, because emission is at higher wavelength, so we take emission minus the absorption maxima. Okay, so it is 360 minus 280. So this is 80 nanometer. Okay. Next one is extinction coefficient of NADH 340 nanometer is 6440 liter per mole per centimeter, whereas NAD does not absorb at 340 nanometer. What absorbance will be observed when light at 340 nanometer passes through 1 centimeter cuvette containing 10 micromolar NADH and 10 micromolar of NAD? Can you guys solve it now? The question is clear or not?
No, ma'am.
Okay, so it says that there is a mixture. Mixture of what? NADH plus NAD, right? There are two substances, two kind of sample in a cuvette, NADH and NAD. The extinction coefficient of NADH at 340 nanometer is given is 6440. Okay, and this guy NAD, it does not absorb. So for this, it does not absorb means extinction coefficient is 0. Now, what is 1 centimeter cuvette means? Path length is L is 1 centimeter for both, because both are in a same cuvette. Both is a mixture. The mixture is in one cuvette. Now, concentration of NADH is 10 micromolar and concentration of NAD, this is NADH, is also 10 micromolar. Now can you solve it? What is the absorbance of the mixture?
Should we have to sum up the concentration of both?
You cannot sum the concentration itself. Absorbance is a additive property. So if you have two substances, the absorbance of both will get added up. Mixture at particular wavelength will be absorbance of NADH plus absorbance of NAD at 340 nanometer at 340. Why I am writing 340 nanometer? Because we have to take the molar extension coefficient at this particular wavelength only. Can you guys do it now?
Yes, ma'am.
Let me know the answer then. So this will be epsilon of NADH into concentration of NADH into L plus epsilon of NAD into concentration of NAD into L. But epsilon of NAD is 0. So this goes to 0. Since NAD does not absorb at 340, it does not contribute to the total absorbance of the system. It's only alleviates absorbance. So it will be 64 liter per mole per centimeter into, it is 10 micromolar, so 10 into 10 to the power 6 molar. Molar means mole per liter into 1 centimeter. Okay, so now it is unitless.
6.4 into 10 raised to minus 3.
Yeah, it is micromolar, no? 10 to the power minus 6. So this is the absorbance of the system. Now, the next question is absorbance of copper sulfate solution containing 0.5 mg copper per ml was reported as this much at 440 nanometer. Calculate the specific absorptivity in including units of copper sulfate on the assumption that 1 centimeter cuvette was used. What is specific absorptivity? It is nothing but molar extension coefficient. It has different names. So A is epsilon times C times L, right? A is given that the absorbance of the sample was reported this much, 0.35. The calculate the specific absorptivity. So epsilon you need to calculate. This much is the concentration, 0.5 mg per ml into length of the cuvette is 1 centimeter. Now you calculate epsilon. Okay?
Okay.
Keep the units. Okay, don't forget the units are here mg per ml. Now the B part is what will be the absorbance if the solution is diluted to twice to its original volume. So this is A1, which is epsilon at concentration C, length L. Now this part, specific absorptivity or molar extension coefficient, this is inherent to the sample, not concentration dependent. Okay, So if you change the concentration, epsilon will not change. So what is A2 at concentration C2? When you say that C2 is diluted, means twice. So C2 is C1 by 2. Dilution means decreasing the concentration, right? So C2 is half of C1. So A1 by A2 is equals to C2, which is C1 by 2 times L. A1 by A2 will be 2. So A2 will be 1 by 2 times of A1. If you dilute the sample by 2 times, the absorbance of the sample should also decrease by half. Okay?
Okay.
Okay, so this is the last question for today. Fluorescence quantum yield and fluorescence lifetime of a molecule are 0.4 and 4 into 10 to the power minus 9 second. So quantum yield is 0.4. Fluorescence quantum yield, it is denoted by the symbol phi. Fluorescence quantum yield is 0.4 and fluorescence lifetime, tau fluorescence lifetime is denoted by the symbol tau, small tau, is given by 5 into 10 to the power minus 9 second, that is 5 nanosecond. If the fluorescence decay rate constant is y into 10 to the power 7 per second, decay rate constant, which is Kr, radiative decay constant, radiative decay rate constant is y into 10 to the power 7 second per second. The value of y is, so we need to find the value of this guy y. How do we approach this problem?
So lifetime and K have relation.
Yeah, what is the relation?
One by K equal to 2.
What is tau? Fluorescence lifetime. Fluorescence lifetime is given by 1 by Kr plus Knr. Remember what is Nr? Non-radiative rate constant. So lifetime does not depend only on the radiative decay rate, it also depends on the non-radiative decay rate. Okay, so lifetime is the ratio of like inverse ratio K of the rate constants of radiative decay and non-radiative decay. And this fluorescence quantum yield is given as Kr divided by Kr plus Knr. Quantum yield, fluorescence quantum yield is the ratio of radiative part divided by the total decay rate. Total decay rate is radiative plus non-radiative. Okay, so you can write it as Kr, since this part Kr plus Knr can be written as tau f. So this part. Quantum yield is, now this is a relation. Quantum yield is equals to Kr into lifetime. Radiative lifetime. So we have been given this quantum yield. We have been given radiative lifetime. We have to find the KR. Okay. Now you can solve this.
Yes.
Let me know the answer then.
Eight.
8. Eight what? So this will come in second inverse, right? Zero 0.4. Here what should I write? 10 to the power? But we have to report in terms of 7. Sorry, this is plus 9. So 8 into 10 to the power 7 second inverse. So here the answer will be 8. Because we needed to find the value of y. Value of y is 8. Okay.
Okay.
So now I'll close this session. Do you guys have questions from today's sessions? Any other questions? Okay. So this the PDF of this PowerPoint will be there in the drive, and that link will be shared to you. And also this session is live on anyway, this session is live, but it is also being recorded, and it will be uploaded on YouTube, and the link of that video will also be shared with you guys later.
Okay.
Okay. So I'll stop this, and next week again, same day, same time, we will have another session. Then there I'll discuss the first assignment.
Okay.
Okay. See you, and thank you for joining.
Thank you.
Thank you.